Welcome to Chapter 11, 11.1, the Fundamental Counting Principle. So it's early in the morning, you're groggy, and you have to pick out something to wear to school. You haven't done laundry for a while, so you are limited to just 2 pairs of pants to choose from, jeans or black sweatpants, and 3 t-shirts to choose from, 1 red, 1 green, and 1 purple. So if you draw a picture of the situation, you might draw something similar to what I have here. So then the next question is, how many choices do you have? So this is called a tree diagram. And what we do is we list all the possibilities and then we simply count 1, 2, 3, 4, 5, 6. 6 different possibilities of an outfit, okay? Because I could have jeans, and from there, if I have jeans, I have 3 different tops I can wear. If I choose sweats, I've got 3 different combinations of tops I could wear there, okay? So this is known as a tree diagram. It's named because of its branches. It looks like a tree. It shows the total number of possible outcomes. Now, we should notice that this isn't very efficient. What if I have more pairs of pants and more pairs, or more t-shirts, and if I have shoes into the mix, or all sorts of different things? What this is leading us into is the fundamental counting principle. So what is the fundamental counting principle? Well, the fundamental counting principle, if you can choose one item from group M items and a second item from group N items, then the total number of 2 item choices is M times N. So for instance, in our example here, we had pants and we had shirts. So I had 2 possible shirts, and I had 2 possible pants and 3 possible shirts. So by the fundamental counting principle, all I would have to do is multiply those options together, and I get the total number of outcomes, or in this case, 6 outfits. So let's take a look at this next example here, dealing with restaurants. So suppose you go to a restaurant and they offer 10 appetizers and 15 main courses. In how many ways can you order a 2-course meal? Now, I certainly could make a tree diagram like up above, but it's much more efficient to use that fundamental counting principle. So I take the number of appetizers I have a choice for, 10, that times the number of main courses. So 10 times 15, I have 150 different ways I could choose my meal for that particular time, okay? So what I want you to do is I want you to take a look at checkpoint 2, and I want you to use the fundamental counting principle to determine in how many ways can you create 2-course schedules. So this is the semester that you will take your required psych and social science courses. There are 10 sections of psychology from which you can choose. There are 4 sections of social science that are available at times that do not conflict with your psych class. In how many ways can you create 2-course schedules that satisfy the psychology and social science requirement? Go ahead, fill it out, and check back. Okay, so hopefully you realized you take the number of psych courses, 10, times the number of social courses, 4, and you get the total number of ways, 40 ways, in which you could create a 2-course schedule. All right, so now let's move back to that outfit. You just realized you forgot about shoes when planning your outfit for the day. Oh no. You have 2 pairs of gym shoes that you can choose from, 1 black and 1 green. Draw a new picture of your outfit choices on the next page. So go ahead and do this and then check back with the video. Okay, so here's our tree diagram adding shoes into the mixture. You can see it's getting more and more complicated. So how many different outfits do we have this time? Well, all we would have to do here is count. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in this case, we have 12 different outfits, right? But again, that's not very efficient. But the nice thing is, the fundamental counting principle still works here. So what we can do is we can take the number of ways in which a series of successive things can occur as found by multiplying the number of ways in which each thing can occur. So in this case, we're just adding more things to our mix. So it's just more multiplication going on. So the total number of outfits, including shoes now, is pants times shirts times shoes, or 2 pants choices times 3 shirt choices times 2 shoe choices, for a grand total of 12 outfits. Okay, so what I want you to do is I want you to use that concept with pizza. Okay, so a pizza can be ordered with 2 choices of size, medium or large, 3 choices of crust, thin, thick, or regular, and 5 choices of toppings, sausage, pepperoni, onions, green peppers, or mushrooms. How many different one-topping pizzas can be ordered? Go ahead, set it up, and see what you get. Hopefully you got 30 different ways, just like I did. So I take the number of choices for my size, I multiply that by the choices for my crust, and multiply that by the choices for my toppings. Multiplying all 3 together, we get 30 different pizzas. Go ahead and try checkpoint 4, dealing with car manufacturers, and see what you get this time. We're just adding more choices of features, so you're still using the fundamental counting principle. Go ahead and give it a try. So this one's dealing with cars. Car manufacturers are now experimenting with lightweight 3-wheel cars designed for one person and considered ideal for city driving. Suppose you could order such a car with a choice of 10 possible colors, with or without AC, electric or gas powered, with or without an onboard computer, and with or without a global positioning system, GPS, for pinpointing your location at every moment. In how many ways can this car be ordered with regard to these options? So we've got 10 color choices. I can either have AC or no AC, so I've got 2 choices there with that. I've got 2 choices dealing with power, electric or gas. I have 2 choices with or without onboard computer, and I have 2 choices for GPS, with or without. So multiplying these all together, I end up with 160 ways that I could order this 3-wheeled car. All right, this next example is a little bit different. It's dealing with multiple choice tests. It has 6 questions. Each of the questions has 3 answer choices, with 1 correct answer per question. If you select one of these 3 choices for each question and leave nothing blank, in how many ways can you answer the questions? So we kind of go through it question by question. It's very similar to everything else. So question 1, I've got 3 choices. Question 2, I have 3 choices, so on and so forth. Each question I have 3 choices for. So I'm simply taking 3 and I'm raising it to the number of choices or number of questions that I have. So I really have 729 different ways in which I could answer these questions. Hope I get them right. So I want you to use this kind of concept. Set up for checkpoint 6. Set up using that fundamental counting principle for a keypad sequence. Read through it, set it up, and see what you get. Check back in a second. Okay, so this one was a little different in the fact that an electric gate can be opened by entering 5 digits on a keypad, 0 through 9. How many different keypad sequences are possible if the digit 0 cannot be used in the first digit? Okay, so I kind of set up my 5 different numbers here, 5 different digits. My first digit, I only had choices from 1 to 9. So I had 9 choices to choose from. But each digit after that, I had from 0 to 9 to choose. So I had 10 choices. So then I used that fundamental counting principle, multiplied all of these together, and I really got 9 times 10 to the 4th, or simply 90,000 different sequences I could make. If you have any questions on this video, let me know, and we'll talk next time we see each other.